The MGM-140 Army Tactical Missile System, or ATACMS, is a long-range guided missile that gives operational commanders the immediate firepower needed to win battles behind enemy lines. With a range of over 300 kilometers, a barrage of ATACMS missiles can wreak havoc on hostile ground formations, artillery batteries, supply depots, communication centers, and other strategic objectives far away from the combat zones. Each ATACMS missile is packaged within a multiple launch rocket system look-alike launch pod, and it can be launched with different warheads to tear apart all kinds of facilities, armored vehicles, and ground formations with devastating effects. What's more, the Army has announced that a more powerful variant is already under development, and it is expected to have a jaw-dropping range. The MGM-140 Army Tactical Missile System, or ATACMS, was developed to replace the aging MGM-52 Lance missile. Introduced into service in 1972, during the last days of the Vietnam War, the Lance was a novelty for its time. The system was envisioned as America's ultimate mobile field artillery tactical surface-to-surface missile, and it could carry both conventional and nuclear payloads if necessary. The Lance had a mass of over 3,500 pounds, a length of 20 feet, and a diameter of 22 inches. The payload comprised either a W-70 nuclear warhead, with a yield of over 100 kilotons, or conventional M251 high-explosive submunitions. In addition, its maximum operational range was up to 75 miles, and it could travel at Mach 3. A Lance system battery of 2 fire units comprised 2 M752 launchers with 1 missile each, and 2 M688 auxiliary vehicles. Plus, the standard fire rate was 3 missiles per hour, no matter the type of warhead used. The US, Italy, Belgium, Israel, the Netherlands, and West Germany all employed the Lance system throughout the Cold War to deter a possible Soviet attack. However, most retired from service in early 1992 when ATACMS was introduced. The development of the Army Tactical Missile System, or ATACMS, began in 1978 when DARPA and the Army worked on the Assault Breaker Technology Demonstration Program. The objective was to attack hostile armor formations using mobile hard targets at long ranges. This was part of Cold War-era doctrines involving all American military branches, and in 1980, the U.S. Air Force replaced the Lance with a similar nuclear-tipped solid-fuel missile. It was dubbed the CISWIS, or Core Support Weapon System. Even so, while the Army and the Air Force continued developing such missile systems, the Department of Defense decided to step in and merge both programs. The result was the Joint Tactical Missile System, or JTACMS, but the Air Force eventually quit because the idea of an air-launched ballistic missile was not part of its strategic employment. Consequently, the JTACMS was redesignated as the Army Tactical Missile System, or ATACMS, and Ling Temco Vought won a contract in 1986 to develop it. The missile was designated MGM-140 and was tested for the first time in 1988. A low-rate initial production contract then started the following year, but further testing and modifications were required before the ATACMS was officially introduced into service in January of 1991 on its way to the war against Iraq. Ultimately, over 32 ATACMS missiles were fired from the M270 MLRS during Operation Desert Storm. And when the United States returned to the Middle East in 2003 as part of Operation Iraqi Freedom, the use of ATACMS skyrocketed, and more than 450 missiles were fired during the operation. In fact, according to Army statistics from 2015, more than 500 missiles have been fired against the enemy after the Americans landed in Iraq and Afghanistan. The ATACMS resembles its predecessor in some ways. Besides the physical similarities, both are deployed from modified multiple launch rocket systems, or MLRS, launch vehicles. There are different variants of the missile, but Block 1 is the standard version of the ATACMS. with a range of 165 kilometers, it can swiftly attack high-value targets such as artillery emplacements, airfields, SAM sites, supply depots, and other objectives located behind enemy lines. Block 1 carries a single 560-kilogram warhead with 950 M74 munitions. They're anti-personnel and anti-material weapons that carry a round ball wrapped in a tungsten fragmenting wall with incendiary pellets and a steel casing. This combination is extremely effective against infantry, lightly armored vehicles, equipment, and support facilities. The total affected area depends on the height at which the missile is detonated. It can either be a small target area with severe damage or a large area with light damage. The Block 1 can be launched from an MLRS-270 AV-MRL and a HIMARS XM-142 wheeled light vehicle, and it began to be phased out in 2009 in favor of the improved Block 1A. This variant has an increased range that varies between 100 and 300 kilometers, depending on the warhead. It can also be equipped with 300 M74 submunitions or a unitary high-explosive warhead. The Block 1A also features an inertial guidance system combined with a GPS that provides an unparalleled level of accuracy. The variant was introduced in 1998, and the Army announced that its service would be extended by 10 years in 2016. The Block 2 was tested in 2002 and was meant to be an anti-tank version of the ATACMS. It was armed with brilliant anti-tank or BAT P-31 improved submunitions or anti-armor BAT guided submunitions. In addition, it had a range of 140 kilometers and carried a warhead of 268 kilograms. However, development on the Block 2 was soon cancelled, despite the critical role it was expected to play against armored vehicles. The Block 3, also known as the TACMS Penetrator, is basically a Block 1A with a range of 250 kilometers and is equipped with an Mk4 re-entry vehicle with a high-explosive penetrating warhead. Finally, the Block 1A Unitary carries either a 247-kilogram high-explosive blast penetration warhead from the SLAM-ER missile or a 25-kilogram AGM-RGM-84 Harpoon warhead. The Unitary has a range of 300 kilometers and stands out because of its intent to minimize collateral damage and attack targets under all weather conditions. Production of the ATACMS ceased in 2007, with a total of 3,700 missiles built by then. However, the Army has been improving the system to increase its accuracy and reliability for new combat scenarios. In 2015, Lockheed Martin was awarded a contract to develop new hardware for the Block 1 and its variants, resulting in updated guidance electronics and other upgrades. Then, in 2020, the Army announced it had conducted the third test of the PRSM, or Precision Strike Missile, the successor of the MGM-140 ATACMS. Although no official information has been shared to this day, analysts speculate that the Precision Strike Missile will have a range of at least 499 kilometers. Other leaked sources indicate the Army placed an order for 54 PRSM missiles with Lockheed Martin for about $78 million in December of 2021, and the Pentagon expects this missile will enter service in 2025. As the war in Ukraine rages on, the nation's government has received countless armaments from NATO partners, especially the United States. Recently, the Ukrainian military acquired HIMARS multiple launch rocket systems, or MLRS. Even so, the armed forces have been pressing the U.S. for more powerful missile systems, such as the ATACMS. The Biden administration has yet to respond to the demands to avoid a direct confrontation with Vladimir Putin. In a briefing on September 15, 2022, the Russian Foreign Ministry spokeswoman Maria Zakharova said, quote, "If Washington decides to supply longer-range missiles to Kyiv, then it will be crossing a red line and will become a direct party in the conflict." The fact that the ATACMS has a range of up to 300 kilometers is the main cause of concern. as this capability would allow Ukraine to strike targets deep inside Russia, and it would be seen as an escalatory measure in the conflict. Only time will tell if the Biden administration will comply with the demands and provide Ukraine with such powerful missiles. In the early 2000s, the Defense Advanced Research Project Agency and the U.S. Navy recognized the need for a weapon that could engage critical targets at extended ranges and do so in extremely hostile environments without relying on precision, intelligence, surveillance, and reconnaissance sources. Since then, the team has developed the Long-Range Anti-Ship Missile, or LRASM, featuring advanced onboard sensing and processing capabilities that diminished its dependency on data links and GPS guidance. The liquid-fueled surface-to-surface missile has an unprecedented potential that will allow highly precise engagement of moving ships based solely on course or initial target cueing. Moreover, its innovative features will enable it to penetrate advanced air defenses, including high-speed and high-assurance lethality. Under an accelerated acquisition contract, Lockheed Martin is further maturing technologies that will bring additional advanced long-range sea and land strike capabilities to the 5th-generation F-35 fleet. With initial fit checks completed and integration efforts going on right now, the Harpoon missile will soon find a worthy replacement. The Defense Advanced Research Projects Agency, or DARPA, and the Office of Naval Research initiated a joint development program in 2008. The endeavor aimed to create a weapon capable of penetrating sophisticated enemy air defense systems from a considerable range. Thus, the AGM-158C long-range anti-ship missile was born. The new system has the capability to engage adversaries armed with anti-satellite weapons, a concerning threat that affected several US-made weapons, like the 1977 Harpoon. Such devices could knock out GPS constellations, blinding the missiles and rendering them less effective. Needless to say, such adversaries are also equipped with advanced air defense capabilities, pushing the need for more significant standoff ranges. Consequently, the new missile was fitted with advanced countermeasures to evade hostile active defense systems. In late June of 2009, DARPA selected its main contractor, and Lockheed Martin received a $10 million contract for a 9-month phase. This initial study phase consisted of concept development, primary design, cost estimation, and analytical support. The program was eventually transitioned to the Navy for a second 27-month phase, covering detailed design, critical design review, material procurement, fabrication, integration, and testing. The demonstrator was ready to support a rapid transition to operational use by 2012, and the Department of Defense estimated the missile would enter service in 2013. Meanwhile, another contract focused on developing an air-launched version that integrated technologies from the Joint Air-to-Surface Standoff Missile Extended Range, or JASSM-ER strike missile. While Lockheed Martin missiles and fire control strike weapons built the LASRAM-A prototype demonstration, the Tactical Missiles Division developed the LASRAM-B1. In turn, BAE Systems Information and Electronic Systems Integration designed the onboard sensor systems, with each division receiving $9.7 million during the first stage. The LASRAM-A team then got $60.3 million to execute 2 air launch demonstrations, and the LASRAM-B team got $157.7 million to create 4 vertical launch system demonstrations for the US Navy. Taking into account its predecessor's legacy, the long-range precision-guided autonomous anti-ship missile was custom-made to meet the needs of US Navy and Air Force warfighters. Thus, it was designed to fulfill their need for anti-surface warfare weapons capability. The LASRAM is armed with a 1,000-pound penetrating and blast fragmentation warhead and employs precision routing and guidance for day or night in all weather conditions. The missile can also approach targets using its self-directing sensing, signature, control, and dynamic response features to defeat air defense systems. Plus, it can be guided by its launch aircraft toward enemy ships from as far away as 200 nautical miles. In addition, it is equipped with a multimodal radio frequency sensor suite for target detection and a weapon data link that not only facilitates communication with operators, but also enables other systems to feed a real-time electronic picture of the battlefield. As a result, several missiles can work together by sharing data and executing a coordinated swarm attack. Meanwhile, an enhanced digital anti-jam GPS allows the missile to detect and destroy specific targets within numerous groups of ships, especially high-priority targets such as aircraft carriers, troop transport ships, and guided missile cruisers. The weapon's sophisticated technology aims to reduce dependence on intelligence, surveillance, and reconnaissance platforms, network links, and GPS navigation when performing in aggressive electronic warfare environments. Hence, advanced guidance enables it to operate on gross target queuing data to accurately pinpoint predefined targets in denied environments and successfully destroy them. Additionally, the weapon includes an electro-optical imaging infrared seeker with automatic scene and target matching recognition that provides positive object identification and accurate targeting for the flight's terminal phase. The advanced targeting systems on board give the innovative machine an upper hand, effectively eliminating the need for prior or precision intelligence or other supporting services that could hamper a mission. Finally, the stealthy missile was designed to fly towards its target at medium altitude and then drop for a sea-skimming approach to counter its objective shipboard anti-missile defenses. Notably, aside from short, low-power data link transmissions, the missile does not emit signals for stealth purposes. Lockheed Martin conducted the first captive carry flight test in the summer of 2012. The trial, conducted at several altitudes and speeds, proved the LRASM's ability to detect, classify, and recognize targets. Designed to be launched from the Mark 41 vertical launch system, the weapon will be compatible with most of the U.S. Navy's vessels and fixed-wing aircraft. Furthermore, it can be fired from outside direct counterfire ranges without sacrificing the maximum possibility of a target hit. In September of 2013, an LRASM booster test vehicle flight successfully demonstrated a launch from a Mark 41 canister, also using the already proven Mark 114 booster. The company pursued the surface launch effort to reduce program risk. Likewise, it was a priority to field offensive anti-surface warfare capability on U.S. Navy surface combatants on an accelerated basis. Remarkably, the missile can be employed from guided missile destroyers and cruisers, with minor software modifications to existing launch control systems. Moreover, the new improvement is both a low-risk and low-cost solution for naval warfighters. The LRASM was expected to enter serial production in 2015, but the missile did not enter service until 3 years later. The SLV variant that will equip the Navy fleet, featuring the Mark 114 and capable of VLS using the Mark 41, was first tested in 2016 with the Tactical Tomahawk weapon control system. The LRASM-A stealthy air-launched subsonic variant, based on the JASSM-ER airframe and incorporating new sensors, entered the first low-rate initial procurement LRIP contract for 23 missiles in the summer of 2017. Additionally, an improved variant known as the AGM-158C2 is expected to be fielded by 2024. Meanwhile, the ship-launched supersonic variant, LRASM-B, powered by a ramjet engine to achieve the desired cruise speed, is expected to be ready by 2025. This version was already heading towards cancellation, but was revived due to a lack of confidence in the Tomahawk. The LRASM can launch from the Navy's FA-18EF Super Hornet and the Air Force's B-1B Lancer. And in early 2022, the Air Force requested Lockheed Martin to build 6 next-generation AGM-158Cs, a job that should be finished within 2 years. In the words of the manufacturer, quote, "Precision lethality against surface and land targets ensures the system will become an important addition to the warfighter's arsenal. LRASM provides range, survivability, and lethality that no other current system provides." The AIM-9 Sidewinder, an enduring symbol of American military prowess, stands as a testament to the longevity and adaptability of military technology. This missile has been a technological marvel for over 6 decades, reigning supreme in aerial warfare. The Sidewinder's impact is not limited to the US. It's the most widely used air-to-air missile in the Western world, with over 110,000 units produced for the US and over 30 of its allies. Its introduction during the Vietnam War marked a turning point, and since then, the AIM-9 has been credited with over 270 aircraft shootdowns across numerous global theaters. But when this iconic missile began to show its age, Raytheon stepped in, securing a contract to upgrade its already lethal heat-seeking capabilities, enhancing lock-on target acquisition and improving effectiveness at ranges where traditional systems falter. The AIM-9 Sidewinder will continue transforming aerial combat for decades to come, ensuring Allied victories in the skies across the globe. The AIM-9 Sidewinder is a legendary supersonic missile renowned for its heat-seeking capabilities and explosive impact. Carried by fighter aircraft, it boasts a high-explosive warhead guided by an infrared heat-seeking system, making it a lethal weapon in aerial combat. Initially developed by the United States Navy for fleet air defense, the Sidewinder was soon adapted by the U.S. Air Force for use by fighter jets. Its early iterations played a crucial role in the Vietnam War, showcasing its effectiveness and solidifying its place in military history. Yet, it was not like this during the humble beginnings of the iconic missile. The AIM-9 Sidewinder was born from a secret experiment conducted in 1945 when World War II ended. A group of engineers at the in Yorkton, California-based Naval Ordnance Test Station were researching lead sulfide proximity fuses that were extremely sensitive to infrared radiation. Then, lead physicist William B. McLean concluded that there was potential for a new kind of missile guidance system. McLean thought that if a proximity fuse could use infrared signatures to initiate detonation, it could also track an infrared signature. In other words, the missile would change its course during flight to keep the target's heat signature reflected onto a sensitive photocell, allowing the rocket to actively seek heat. The idea was innovative, but the problem was that McLean's hobby shop was not in charge of designing weapons. However, that did not stop the team from going forward and experimenting. McLean, unfazed by his peers' skepticism, led his team in the development of an innovative infrared system to guide standard 5-inch air-to-ground rockets. Getting it right was tricky. It needed to be reliable, which meant minimizing the required moving parts. By the 1950s, the US was already at war in Korea, and the Navy and Air Force soon realized that the MiG-15 fighters were outclassing most Allied fighters. They turned to the history books and remembered the Germans had invented air-to-ground missiles during World War II. Then they found McLean and his team. The team had already developed the prototype of their missile after more than 5 years of meticulous studying, with McLean later writing, quote, "I spent nearly 3 years just considering possibilities. It's easy to build something complicated. It's hard to build it so that it's simple." The final design of the AIM-9 Sidewinder missile was indeed simple, yet it turned out to be highly effective as well. It featured a parabolic mirror spinning gyroscopically at an impressive speed of 4,200 revolutions a minute within the transparent nose cone of the missile. This spinning mirror played a crucial role in detecting and tracking the infrared signature of a target. As the missile flew through the air, the parabolic mirror would reflect any infrared blips or heat signatures it encountered. The position of these reflections on the mirror indicated the angle at which the target was located, relative to the missile's axis of spin. The further the reflection from the center, the greater the angle of the missile's flight path. At the heart of the system was a lead sulfide detector. It continuously measured the infrared reflections and generated a current proportional to the heat signal's strength and position. This current controlled electromagnets positioned around the mirror's rim, which adjusted the missile's canard guide fins, small control surfaces on the missile's body. The missile could alter its trajectory by constantly adjusting these fins, effectively steering itself toward the heat source. This ingenious mechanism allowed the Sidewinder to maintain a lock on its target, ensuring accurate mid-flight course corrections and significantly enhancing its hit probability. To prevent interference with the gyro's spin, McLean's team developed rollers, gyro wheels mounted on the tail fin and driven by the airstream, which countered the missile's movements.
Additionally, they wired the seeker to aim not at the target's current position, but at where it would be. This allowed the missile to engage enemy aircraft on its own terms, seeking them out, pursuing them, and outmaneuvering them during dogfights. McLean baptized this groundbreaking missile design as the Sidewinder, a poisonous snake that dominated the Mojave Desert close to China Lake. It was a fitting name, but this snake hunts down its prey by sensing its body heat. Future astronaut Wally Schirra, a skilled Korean War veteran with a MiG-15 shoot-down behind him, recalled his first visit to McLean's lab. He described the Sidewinder as a dome-shaped device made of glass, which he called a man-made eyeball. He mentioned being a cigarette smoker at that time, and how he noticed the eyeball tracking his movement as he crossed the room. McLean's team ushered in a new age of technological innovation with an object that comprised 14 tubes, less than 24 moving parts, and measured less than 10 feet long and 5 inches across, with a weight of around 160 pounds. The Sidewinder's unique design also pioneered another aspect of military technology. Its onboard guidance system was far more sophisticated than the computers that occupied entire rooms. The missile was, in other words, an almost fully automated robot, conceived for destruction. The prototype was tested in 1953, with test pilots left in awe after noticing they could easily lock in not only flying target aircraft, but smaller objects like buses, trailers, and small locomotives around China Lake. In 1956, the Sidewinder was taken to sea for use with carrier aircraft, with U.S. Navy Lieutenant Commodore C.A. Tierney later bragging, quote, "It's like having a 6-foot reach on the other fellow in a boxing bout." 2 years later, the U.S. launched Operation Black Magic, supplying the Republic of China Air Force F-86 Sabres with top-secret ordnance. The enemy was utterly unaware of the Sidewinder. The Communist Chinese and the Soviets were confident in the superiority of their MiG-15s and MiG-17Fs, but soon found out about the hidden ace up the Sabre's sleeve, the heat-seeking Sidewinder. While the enemy was faster and could fly higher, the Chinese pilots were bewildered by the devilish missiles that followed them anywhere, no matter the evasive maneuvers they tried. One after another, they went down in a skirmish, caught by surprise. The airfight was a complete success for the Allied Taiwanese. It proved to the U.S. that the Sidewinder was the next step in the evolution of air warfare, ensuring a series of variants that would make it more lethal and effective for future wars. Decades later, Major Justin Hassard Lee, a U.S. Air Force F-35 pilot instructor, would summarize how the Sidewinder revolutionized air warfare, stating, quote, "We no longer had to get to the perfect place in space and time to allow a bullet to hit another aircraft traveling 500-plus knots, but rather just had to get behind the enemy aircraft generally." While the Soviets were hard at work trying to reverse engineer the Sidewinder and would eventually come up with the Vimpel K-13, the U.S. was already developing advanced variants of the original design. The Sidewinder remains in service almost 70 years after its first launch. However, given its many upgrades, it's virtually unrecognizable from the variant that first flew in the 1950s. Since then, the Sidewinder has seen plenty of combat in several wars, including the Taiwan Strait Crisis, the Vietnam War, the Falklands War, and the Gulf War. Over 110,000 missiles have been produced so far, and the Sidewinder has been verified with more than 270 aircraft kills. The latest shootdowns of a Sidewinder, the highly advanced AIM-9X, were verified in February 2023, when a U.S. Air Force F-22 intercepted a Chinese spy balloon in Surfside Beach, South Carolina, at an altitude of 60,000 feet, and took it down with the legendary Sidewinder, claiming the first balloon missile victory. Today's highly advanced Block II AIM-9X missiles, which entered service in 2015, represent the pinnacle of the Sidewinder's evolution. These cutting-edge missiles can be used over the horizon, enabling pilots to fire without a lock and allowing the missile to acquire its target during flight. Remarkably, they can even attack ground targets like tanks without any modifications. The Sidewinder remains the most widely deployed air-to-air missile in the world, equipping American fighters from the venerable F-15 to the state-of-the-art F-35s. Who could believe this incredible milestone was achieved from an inside program that came out of McLean's hobby shop, and not the top-tier engineers of the arms industry of the Cold War? Introduced less than a decade ago, Lockheed Martin's Terminal High Altitude Area Defense, or THAAD system, is now a critical element of the United States ballistic missile defense system. With its ability to intercept and destroy ballistic missiles both inside and outside the Earth's atmosphere as they descend towards their target, the program is one of the company's greatest defense successes. During its first decade of service, THAAD had an incredible 100% success rate, with 15 successful intercepts in 15 attempts. And while a relatively new weapon system, many countries' armies have expressed particular interest in deploying it. However, several nations are highly alarmed by the technology, and it almost cost South Korea its cordial relationship with the mighty Red Dragon. The Terminal High Altitude Area Defense, known as THAAD, is an American-made anti-ballistic missile defense system, one of the latest United States innovations in defense technology. Targeting short, medium, and intermediate-range ballistic missiles, THAAD's overall operation is similar to other surface-to-air and missile interceptor systems. However, a clear differentiator is that the Lockheed Martin design intercepts the devices while they're in their descent stage. After an X-band active electronically scanned array radar kicks off THAAD's interception and detects the target projectile, the system's fire control and support equipment identifies, verifies, and initiates the launching process. The system's mobile erector launcher then releases the infrared seeker head-equipped THAAD missile, which intercepts with a hit-to-kill approach. According to the system's manufacturer, Lockheed Martin, instead of an actual warhead, THAAD relies purely on the kinetic energy of the impact to destroy the incoming enemy missile in downwards direction, with its destructive power coming from the high velocity and not an ammunition load. As such, the THAAD system is designed to provide a robust defensive shield to protect high-value strategic or tactical sites, such as airfields or populated town centers, against a mass raid. While the actual data for Lockheed's system is classified, according to estimates, THAAD systems have an estimated range of 125 miles and can intercept enemy missiles at both endo and exo-atmospheric altitudes, with a maximum altitude of 93 miles above the Earth's surface. And it does this while traveling at incredible hypersonic speeds of Mach 8. According to 2015 estimates, a THAAD battery system consists of at least 6 launcher vehicles, each with 8 missiles, 2 mobile tactical operations centers, and a ground-based radar, costing $800 million per battery. Developed after the experience of Iraq's successful Russian-made Scud missile attacks during the 1991 Gulf Wars, the United States Army began the program development and risk reduction phase of the THAAD systems the following year. Then, after thorough research, the THAAD program entered the engineering and manufacturing development phase at the turn of the century. From its beginning, the development of the anti-ballistic missile defense system became a resounding success for both Lockheed Martin and the United States Army. Separate flight test trials began in 2004 at Lockheed Martin's production facilities in Alabama and White Sands Missile Range in New Mexico. The first flight test of the entire system, with missile, launcher, radar, and fire control system, took place in 2006, and a successful intercept test in the high endo atmosphere occurred the following year. Despite initial plans to deploy the system around 2010, the successful tests caused an involuntary expedition. In early 2007, Lockheed Martin was awarded a contract for the first 2 production THAAD systems, which were completed 2 years later. Then, in May of 2008, the United States Army activated the first THAAD battery unit, followed by the second in October of 2009. Follow-on contracts for the continued development of the system and associated support equipment continued through the 2010s, and by the end of 2015, 5 Terminal High Altitude Area Defense batteries were active in the United States Army. In addition, the service opened a THAAD training center at Fort Sill, Oklahoma that same year to facilitate the use of the thriving program. In 2012, the United States Defense Security Corporation Agency approved the sale of the Terminal High Altitude Area Defense to both Qatar and the United Arab Emirates, marking the first foreign military sale of the weapon. The United Arab Emirates began training units that same year, and the nation became the first to use the systems in a military operation in early 2022. During a dangerous attack by Houthi militants, an Islamic insurgent group in Abu Dhabi, the Terminal High-Altitude Area Defense System intercepted and took out a mid-range ballistic missile used to attack an Emirati oil facility near an airbase. The attack used cruise missiles, ballistic missiles, and drones. The Emirati embassy in Washington, D.C. did not respond to a request for comment, and the events were only confirmed through anonymous external sources. The system has been continually deployed around the world since then, including in Guam, Israel, Japan, and South Korea, with multi-billion-dollar deals. A home run for Lockheed Martin. The company achieved the milestone of delivering 100 interceptors to the United States and its allied nations in July of 2015. Still, not all nations are happy with the existence and use of this powerful weapon. Discussions between the United States and South Korea to acquire THAAD systems began in early 2016 due to North Korea's growing nuclear missile threat. Soon after, China's ambassador to Seoul implied that the deployment of the defense system could potentially destroy relations between South Korea and China. Instead of the powerful kinetic punch, China's main worry regarding THAAD is the system's surveillance capabilities. According to the spokesperson, the use of THAAD would give Washington earlier warning and tracking of Chinese intercontinental ballistic missiles, thus downgrading the nation's ability to target the United States. Even Russia was threatened by the ballistic missile defense radar and denounced its use in nearby European nations like Poland. Once the negotiations between the United States and South Korea were in full swing, China wasted no time implementing informal sanctions against various industries. Such economic pressure against South Korea was meant to reverse its decision. Because the THAAD system was deployed on a piece of land transferred from Korean grocery store chain Lotte to the South Korean government, the company inadvertently became the epicenter of the geopolitical dispute. Consequently, Beijing implemented an informal ban on group tourism travel and went as far as staging a public bulldozing of Korean spirit bottles. Even Korean cultural exports, like K-pop music and K-dramas, once a mainstay in Chinese popular entertainment, were largely erased from content platforms, and several artists faced visa restrictions. To relieve the economic strain on the targeted South Korean industries, as well as to normalize the relationship between the nations, a new administration began to negotiate a solution to the impasse in the fall of 2017. The agreement between China and South Korea called for the resumption of normal economic relations through the commitment to the Three No's plan. This deal prohibited any additional deployment of THAAD batteries, no South Korean integration into the United States-led regional missile defense system, and no trilateral alliance with the United States or Japan. From then on, the Chinese and South Korean relationship has significantly improved. Nevertheless, while the renewal of regular connections has seen an uptick in Chinese tourists in South Korea, the sanctions put in place can still be felt to this day. It is estimated that the South Korean tourism industry may have lost up to $24 billion because of the implementation of the THAAD system. According to cultural experts, the dispute over the Lockheed Martin weapon may also have helped spur some of the growth seen in South Korean culture in other countries, including America, as it forced the industry to look to other markets. After an efficient 24-month campaign, the Air Force took a decisive step and brought a millenary relic into the 21st century, the Rapid Dragon. With a modernized system of palletized projectiles, the weapon is expected to provide the upper hand for the United States defense in any conflict around the globe. This new palletized munitions system is being developed to launch a series of missiles from cargo aircraft, such as the C-130 and C-17, without having to modify them, and allowing them to drop the weapon and carry on with their mission. A successful test carried out with live munitions in late 2021 proved the efficiency of a weapon that ancient armies never even dreamed of, taking a step forward into the future of warfare. About 1,000 years ago, the Chinese military developed a devastating and staggering weapon in which entire armies could be neutralized under a rain of destruction. The so-called Jilong-che, or Rapid Dragon carts, were multiple crossbow bolts launched simultaneously by a single trigger. The powerful concept endured and evolved over the centuries, and the US Air Force has just brought it to life again, only with modern, high-end technology. The Air Force version of the Rapid Dragon is an airborne delivery system for 21st century weapons. Not unlike its ancestor, the new pelletized munitions system has the potential to unleash an avalanche of salvos on top of remote adversaries from aircraft that can then continue with further missions. The Air Force Research Laboratory's Strategic Development Planning and Experimentation Office's project is an experimental campaign dealing with pelletized munitions and their operational advantages. The project's main focus is to allow these long-range weapons to be airdropped from existing airlift platforms, like the C-130 and C-17, without modifying current aircraft. Pelletized munitions are traditional weapons airdropped from existing cargo aircraft by a custom-designed deployment box on a standard airdrop platform. Its roll-on, roll-off capabilities enable rapid fielding while avoiding aircraft modification. By rapidly deploying pelletized munitions, the airspace can be saturated with multiple weapons and effects, thus complicating rival targeting solutions. Moreover, the ploy could help in critical target prosecution by opening access and depleting the enemy's munitions stockpile. Furthermore, pelletized munitions could be helpful in sea mining missions, restricting sea lane or harbor activities, and facilitating adversary cost imposition by driving a reallocation of resources under a new concept of operation. Also, its capability as a force multiplier can be extended to partners and allies, further expanding the reach of American defenses in case of limitation across different scenarios, including aircraft availability. Rapid Dragon's benefits are threefold. Tactically, pelletized munitions provide overwhelming mass. Operationally, they free fighters and bombers for other key missions within the area of responsibility. And strategically, the weapon enables specific bombing capability to both foreign partners and allies, as well as across US services, thus reducing the cost imposition curve. Plus, it is a potent means of deterrence. While current efforts have focused on a 6-weapon configuration for the C-130 and a 9-weapon configuration for the C-17, the Rapid Dragon is not limited to such standards. In fact, it can be refined to increase payload capabilities with other weapon systems. The multi-phase program has brought together stakeholders from across the Department of Defense, the Air Force Major Commander's Test and Evaluation Enterprise, program offices, and the engineering industry. The project has already undergone the mandatory phases, from modeling, simulation, and analysis to demonstration and flight tests. It was established in December of 2019 and was expected to reach powered flight within 24 months, and they succeeded. On December 16, 2021, the US Air Force managed to destroy a target in the Gulf of Mexico during the first live-fire demonstration of the Rapid Dragon program. The final flight test at Eglin Air Force Base in Florida marked the beginning of a new era in military history. The sheer possibility of transforming cargo aircraft into potent armed bomb trucks would suffice to reimagine warfare. The Air Force executed a similar test a month before, although with an unarmed long-range cruise missile separation test vehicle. However, in the December test, the cruise missile carried by an MC-130J Commando 2 was armed, and the aircraft battle management system was fed new targeting data in flight, which was routed to the flight test vehicle. It was the first time new targeting data was received and uploaded to a live cruise missile during flight. Once the MC-130J reached the drop zone, the crew deployed the pelletized munition system loaded with a single cruise missile and 3 mass simulants. The system then parachuted into stability as the missile and dummies were subsequently released, thus avoiding collisions. The way the missile was deployed was unconventional, as it did so vertically, pointing down. Next, the missile sprung its wings and tail, and as it regained aerodynamic control, it started its engine and pulled up towards the target, destroying it upon impact. With this precedent, the Air Force Research Laboratory, or AFRL, hopes to prove that the system can work with other aircraft types, and a follow-up experiment is scheduled for the spring of 2022 to test the weapon with the C-17 Globemaster. In theory, the retargeting methods developed for Rapid Dragon should be adaptable to other platforms. The Air Force also expects to amplify Rapid Dragon's capabilities to house additional weapon systems, and the developmental prototype should be operational by 2023. According to the AFRL, Rapid Dragon's quick development was an example of government and industry collaboration. And in the words of Dr. Dean Evans, Rapid Dragon's program manager, quote, "Rapid Dragon was able to accelerate development by building a broad and strong team. We were committed to a test often, learn fast culture, dedicated to experimenting frequently and taking calculated risks. In addition to the MAGCOMs and air staff, the Rapid Dragon team included the developmental test and operational test communities, the aircraft and weapons program offices, and the mission planners. This collaboration from the onset streamlined the process and accelerated development, including groups from the program inception that are not normally included at the very early stages, and that has made all the difference. The Enterprise's measure of success came from the design becoming a system-level flight test within 10 months, and a live fire test only 5 months later. Also, over the last stretch of 2021, Rapid Dragon was tested on 2 different models other than the MC-130J, the EC-130SJ, and the C-17A. During the program, the AFRL Strategic Development Planning and Experimentation Office cooperated with its partners, Air Force Futures, Air Force Special Operations Command, and Air Mobility Command, and completed 4 phases. First, the concept feasibility was proven, as was the capability of the aircraft and joint air-to-surface standoff missiles in palletized configurations. Then Command and Control, C2, fire control, and mission planning involving targeting and retargeting were developed. Simulation and ground tests subsequently validated deployment system designs and stability. And finally, high-altitude drop, jettison, and deconfliction of payloads during operation paved the way for powered flight tests. Major General Heather Pringle expressed that, quote, "This type of experimentation campaign that addresses capability gaps and demonstrates transformative efforts helps us shape future requirements and reduces timeline to fielding. This approach ultimately enables a rapid fielding alternative to traditional lengthy acquisition timelines." Such successful achievements as the Rapid Dragon's expedient development promise a dramatic increase in the availability of fires for combatant commanders to reach even more enemy targets for both US and Allied mobility platforms, paving the way for a new type of warfare.